I'd like to turn it over to my friend and colleague Arun Pamulapati, who's going to take you through actually a live demonstration of how we build this capability and give you a sense of what it takes to make it work. So Arun, let me hand it over to you.
Thank you, Howard. I'm going to share my screen and hopefully you can see. Thank you all for joining this morning. Welcome to Databricks Unified Analytics Platform, where your data engineers, data scientists, and security analysts can collaborate to extract value from the data and secure your organizations. To perform any type of analysis, first you are going to need compute resources. So I'm going to click on clusters, and I'm going to quickly walk you through how you can provision quickly that infrastructure that Howard was talking about anywhere in the cloud. So with terabytes of RAM and hundreds of computers, CPUs, basically doing threat detection at scale becomes practical. And with Databricks optimized runtime Spark, with Delta, that performance that you're looking for and that cost effectiveness that is needed to do the analysis at scale actually is actually possible. So I'm going to go ahead and create a quick cluster. And within 3 minutes, you will have this compute environment. One of the important things that you get with Databricks is that your compute environments can be of different shapes and sizes, of different versions. The reason that is important for you is that as part of the architecture for building threat detection data lake at scale is you are going to need different sizes of environments for ingesting and to do ML. And at the same time, when you have an incident to do incident response, you want to make sure that you have enough resources to get to the bottom of that situation where you do not want to disturb existing workloads and at the same time be effective with your work. So with the ephemerality we bring, as you can see, I have many clusters here running. And also, when these workloads are done, they get terminated, you are going to get that cloud auto scale and cloud overall performance at the same time having that flexibility of using different sizes of workloads at scale, right? So once you have the compute environment, the next thing that you're going to use is the workspace. With Databricks Workspace, you are actually be able to quickly get to algorithms that you want to build. So here, I'm in my notebooks environment where I'm able to collaborate with my colleagues and start building an ingestion pipeline. So let's look at very high level the architecture for building this threat analytics data lake architecture. The first thing is going to be taking in all those types of data logs that are coming from your systems, right? So at the top, you see that you may have some bro logs set up to ingest your network logs. They're going to be tab-separated files, and you may have Snort applications running to take in your NIDS logs, which tend to be binary files. And you may have some modern logs that are coming from your cloud infrastructure for audits. Here you see AWS CloudTrail as an example, which is a JSON format file. And as Howard said, we have many connectors to different systems. In this case, we can actually ingest from Splunk using their JDBC to get the data. So the reason this is important is when you have these different types of log files in silos, and if you are trying to find a specific anomaly, it's very hard to find that needle in the haystack. To find the needle in the haystack, you kind of need the whole haystack. So this is what we are trying to accomplish here by getting all kinds of logs, which are in different formats. Spark lends itself very well, and using Delta capabilities to reliably ingest that and then land that into economical storage, in this case, that is S3. And the good, because it is economical, good news is that you can keep that all of your data for as long as you want it. So that's your historical data, and continuously ingest the streaming data. And once you have the lake that is actually performant to do different analysis, you actually can move from creating these expensive systems that are actually going to keep only the data for 2 weeks. Move away from that and have all of your data ready for queries. So at this point, you can actually start building some descriptive analytics and also refining this data using the models, right? So you can train the models on this data set from the historical behavior of your users. And once you have these models, you can actually now productionize those models. What that means is you learn from your historical user behavior or your network logs based on different types of activities that are happening, and identify what an anomaly is. And then you can continuously score as the events are coming in for the live activities. You can actually now further refine and say, hey, based on the historical behavior, as for this model, I am now predicting that there is a certain anomaly, and then produce those alerts, right? So in this case, I can take advantage of Databricks jobs and then continuously look at these logs that are coming in and generate these alerts. So these alerts can be of different types. One is these alerts may be enabling some of your dashboards that are required for your daily reporting. So these dashboards can be giving you 360-degree view of what's happening within your infrastructure. And other alerts can be summaries that are going back into your your SIM tools that are also collecting from your existing log pipelines. So they can aggregate from your historical data, and they can continue to produce some of the reports that you are already taking advantage of. The next one is you can be proactive about it, and if your alert or a specific anomaly is high enough, you can now generate a PagerDuty alert to someone to actually dig deep into the situation and find what's happening, right? So that's at a very high level, being able to produce an architecture where it is scalable, and at the same time, the queries are performance for your business speed, so that you can actually be proactive about your network infrastructure. So along the way, what I'm going to do is I'm going to show you examples for each step of the architecture. So as you follow with me, I'm going to highlight each stage with a red rectangle here. So first step, what we are going to do is we are going to unify information from multiple data sources that are in many different data formats. So for this example, we are going to use FTP logs, HTTP logs, and also some CloudTrail logs, and we are going to put them into a Delta Lake. And so as a first step, as you can see, I have some connection logs, and then I can actually head that out and look at what those logs are. So that's a very important step to kind of make sure that I'm actually looking at the right thing. And here, what I'm seeing is there is these are tabs separated. There's some information, so I can actually look at that. And there is some IP addresses, and the traffic type is TCP. So the next logs I want to look at are FTP logs. So I'm going to go ahead and look at those logs and what they are saying. In this case, similar to my connection logs, but I also have some binary data coming in, and I have some timestamps around that. But these logs are kind of readable at this point, but not queryable. So I have some work to do against those logs. The next set of log types are my SSH logs. So it's the same story here. These are tabular. They're all separated by the tab, and I have some source and destination connection information, and some timestamps again. So at this point, the step that we are going to do, and this is pretty common, having worked on processing these logs for about 7 years. The first thing is like, how do I clean and cleanse and enrich this data, right? So that I can actually prepare this data for processing for the downstream. So I'm going to load this data with a single command very quickly, and then make a data frame out of that. So what data frame is? It's an in-memory representation of my log file. So with like 2 lines, the log file from here, where it is simple readable, I'm able to get into a tabular format with meaningful headings, and at the same time, it is now actually queryable, right? So in this case, I kind of formatted that to, because these log files are very well-published APIs, I know what the schema is, and we can share all those schemas to pass these logs and also give a structure to that easily with you, and we do that all the time with our customers. So now at this point I have a good structure, but I see that there is some empty values which are not going to be helpful for me. They're only taking up a lot of space, and also my time is not useful for me in this format. So I'm going to do a simple ETL. So ETL process is very important to enrich your data, to make it much more useful for downstream applications. So I'm going to kind of go ahead and use my Python capability. So notebooks is nothing but some series of cells which are, these code blocks can be executed independent of each other. So I'm going to write a simple Python script here, and I'm going to clean up those empty cells, and I'm also going to format my date that is much more human readable, right? So with that, now the data frame that I loaded for connection files is pretty clean. Now I can actually see the dates, and also my date formatting is as per my need. And I also replace those empty values with null, so that I am not spending too much storage costs for nothing, for empty values, right? So this is a quick example of how you can actually parse out and ingest those different types of data, which is in different formats. And once I have that, now I can continuously ingest this into Delta, Databricks Delta Lake as a streaming. Streaming, as Howard said, is very important because these log events are continuously happening, and my goal is to not do a nightly batch. My goal is to kind of act upon those events as they are happening, right? So at this point, I am ingesting, with less than, if you even count the white lines, with less than 22 lines of code, I'm able to ingest 3 different types of logs, which are coming from 3 different systems, and continuously monitor what's happening, individual pipelines, individual streams, right? So notebooks are tightly integrated into Spark and Spark streaming and Delta streaming. So with this, you are never going to lose any of your status on what's happening to your individual logs, and you will get full visibility of that process, right? So as I was going along, you might have observed there are a couple of things happening. The first thing is I am using different languages in each of these cells. Here I was using Python. I'll show you an example of doing SQL. So that's one of the important capability as part of the building these threat detection models. In the beginning, the data engineering is going to happen either in Python or Scala, and later on you are going to see me building this and making these log files that make available for people who do not know how to code in Python or Scala, right? There are a lot of other skills that your analysts are going to employ, and we want to make sure that the platform is available for all those personas. So in this case, as you can see, if I do not understand such a log file or something, I can call help. And as Howard said, Databricks notebooks are collaborative, just like Google Docs. So here my colleague Zafar is here in this cell and trying to, he's ready to help me. So if I don't understand certain log format, you can say, hey, what do you think about these log files? Are these the right log files for us to build the system off of? Another thing is, we can comment with each other. So this makes your whole process of building workloads very easy in a collaborative way. You don't kind of discover that you're using some wrong input sources after building the whole system. So you can actually collaborate with each other, and the revision controls that are available. So that you're going to get in kind of in out of the box versioning so that if as you're making progress in your project, you have that too. So at this point, we looked at traditional log files. Let's look at how the process of getting some of the advanced logs, like the ones that you tend to see in the cloud. In this case, I'm going to show you the CloudTrail logs. So I'm not a expert in AWS or by any means cloud certified guru or something. When I started actually wanting to ingest CloudTrail logs, all I had to do is just go online and go through the documentation for basically configuring the CloudTrail logs, and then creating a SPS queue so that that the data is available from my cloud infrastructure VPCs, and then within few lines of code I was able to get into Delta Lake. The whole thing to set up took me for less than 3 hours, which surprised me because the whole process of setting up these steps is so easy. So it would be shame if we are not taking advantage of these infrastructure standardized APIs and have the logs ready so that if an event happens, you are not being reactive. And as you all know, the logs, you cannot go back and create logs if you do not have them available for you. And so if you have any questions about setting this infrastructure of how to configure CloudTrails and creating these queues so that your logs are available, please reach out to us. We are here to help, and we have very simple one-page documentation of setting this up, right? So I have my CloudTrail logs configured, and those CloudTrail logs are landing into S3. So if anybody does anything like creating an EC2 machine, or going and adding a file to S3, or reading a file from S3, everything gets logged and made it available. And also it generates a queue event as JSON file, right? And this queue is available. And the good news is Databricks actually implemented a connector and a custom mechanism to effectively read from these queues. So I am basically plugging into that queue, and all it takes to read that is basically a few lines of code to get those messages that are coming in JSON format, and then we have a standardized parser. Again, this parser will work for you because again CloudTrail logs are standard, so your CloudTrail logs will be similar to my CloudTrail logs. So with this code in your hand, you are ready to actually create readily queryable CloudTrail logs in your infrastructure, right? So I can continuously monitor, as the events are happening in my CloudTrail. That's peace of mind for me. And now that these logs are landing into CloudTrail, Howard touched upon many aspects of Delta. One of the important aspects is having this ACID compliant transactions. What that means is, as the events are arriving, right, as the JSON events are arriving at this queue, we are ingesting into Databricks Delta. If for some reason, if a connectivity is lost to that queue, what you do not want to end up is a half-written JSON file, because that will break your downstream applications. So ACID compliance means, either Delta will write your full parsed out JSON file as a table onto this cloud location S3 and make it ready for queries, or it will roll back. It will not write half JSON files into your S3, right? So at this point, I have my CloudTrail logs landing into this location with a couple of lines of code. I'm able to get that those log files available as a table. This is the power of being able to support multiple languages in Databricks. So at this point onwards, you not only have the logs that gives you peace of mind if an event happens, but also they are queryable. This is a huge important step. I highly recommend whenever one of our customers say, Arun, where do we start? I say, first start ingesting all of your logs and have them available in the cloud storage for queries. That way, you have a plan for how to act from the point of view of analytics, right? For example, if as part of the process of quickly checking what's happening inside of my logs, I can start querying this just as if it is a simple table, right? So in this case, if I want to look at all the logs, I can put a simple filter of date and then say, hey, I want to have a simplified table that is actually looking for only logs since that date, and I want to skip through every single other file, other log that happened before that to get started with, right? So I have 16 million plus events since that date, but that's not all we do. So at this point, once you have these tables readily available, Databricks Delta, makes these queries go fast and at massive scale. For example, if I want to, query a very, very important, specific events that are happening, I can write a simple business level language query as opposed to parsing out low level logs. In this case, I want to identify all the errors in my log files for a given day. All I have to do is know a simple SQL. I'm no longer writing programming language queries. In this case, a simple SQL will suffice, and that gives me very quickly all these events that are happening, all the errors that happen on the day. And if I want to identify things like if anyone is accessing my S3 buckets without identifying themselves. Usually organizations have policies that you need to have proper authentication, authorization, and you do not want to leave out your S3 buckets with customer data without with access to anyone. So the most important thing is you want to identify such access things and then so that you can lock them down. At the same time, you can change this query simply, something like, are there any S3 buckets out there with public access? Right. So, in this case, I want to see 0, which is good. So all of this is possible because, as Howard mentioned, Delta, as the data is getting ingested, picks up on, different things. Like, it is a columnar storage. It is Parquet in an open kind of source format. As the data is arriving, it maintains simple statistics that are common sense for each of those columns. For example, if I want to query a very pointed for a specific event, when I run this query by event ID for a given date, it will only read the files that have this specific event and that falls for this particular date, and it will skip through all the rest of the petabyte data that I have on this S3 bucket, which is huge savings for obviously for S3 reads, but also it kind of changes the interactiveness and performance for getting these results very quick to me in a situation where I don't have too much time to kind of go through the whole petabyte read, right? So at this point we have CloudTrail logs and we have connection logs. So from my enterprise perspective, I have my first step of basically a petabyte scale storage and query system, and the data is now ready and reliable and performant for queries, so that now I can focus on advanced analytics and online scoring, and also for impact analysis, for ad hoc analysis. So once you have this lake, the next step is like, how do I automate this process, right? And how do I take advantage of, these streams that are coming in and live score them? So for that, we are going to take advantage of Databricks jobs on this streaming data. So let me quickly jump to that. Here in this case, when I get to this specific job, you will see, you can schedule the jobs and run on the infrastructure for continuously looking at these events that are coming in. So Databricks jobs is, easy to kind of create on a specific schedule and run a specific flow of activity, right? So you can, as you have a lot of control here, like, of what size of compute environment you are going to use for running this job. But, at some point, you want to make sure you have the visibility without babysitting these processes. So for that, you have ability to configure different alerts, right? So in this case, I am alerting myself if a job fails, I want to get notified. But you can have different, kind of scenarios where you want to make sure you are getting informed. So at this stage, I have a streaming job, and it is continuously reading through my CloudTrail logs as they're coming, and I'm going to score them of a specific anomalous behavior. And therefore, who is going to follow me in a bit is going to show you how to write such models by taking advantage of advanced ML capabilities that Howard mentioned a bit ago to build these models, right? So I'm taking that function that is available for me, and then I'm automating the process of looking at these events as they are coming. So I'm windowing by every 15 minutes. I'm looking for anomalous behavior so that, after, at a certain risk factor with a probability of 60%, I want to generate this alerts delta table. So, we are continuously looking at these events and we are generating these alerts, right? So these alerts can go into dashboards and, and also the summaries can go into your, other traditional SIEM tools. So for that, to complete that loop of taking data from, your SIEM tools and making sure, you are collaborating with everything else out there in your network infrastructure, and then pushing down some summaries to your SIEM tools. Once I have these alerts, I'm also going to read that alert in a stream fashion. So I'm picking up those alerts and I am deduplicating these, and I'm going to generate some pager-duty alerts, right? So in this case, like, I want to, produce an event to a triage person, so that, they're aware of a situation that they can actually go ahead and do some impact analysis. So I have these jobs configured, and they're continuously going on, and they're producing data into these tables. Let's look at how we can take advantage of the summaries that are coming in and a dashboard. So with the dashboarding function that I have here, I should be able to continuously monitor the important information aggregations of my network, and look at things like where are the connections coming from, what type of events happening in my platform. And continuous monitoring of access to whatever your reporting needs are. You can actually have those continuously queried and made them available as a visual display. But at this point, one of the important things I'm seeing here is that algorithm that I have is detecting a specific event as anomalous with a risk factor of 0.82. So this is a kind of a place where I would need a runbooks. So what that means is I need to be able to quickly respond to something of this event, and we know that this event happened on March 18th. So that gives me a quick window. So I want to basically take advantage of the runbooks that I have, and I'm going to use an existing runbook to get to the bottom of a situation. So in this case, I have a runbook that is available. So I am responding to that. But I'll also quickly walk you through a situation where you may, if you don't have a runbook, right? So in this case, I just by changing the input window, I'm working through the process, and I'm actually kind of able to quickly get to the bottom of a situation that's happening. So each of these threats can be different, and what I would need is ability to quickly respond. So you can actually if you have a runbook and if you want if your new alert is different from what you are aware of, and you want to triage an investigation, you can start by cloning these notebooks, and you can a new center of excellence around how do we respond to a new threat, right? So for that, you're going to need a collaborative environment. So first, let's take this alert that we got. We know that this is for a window of March 18th. So I'm going to take that date, and then I'm going to narrow into that the logs that are meant for that, right? So Delta makes that whole process easy for me, and now I have a quick way of getting to only those logs, not the entire petabyte, and I can start querying this. So in this case, what I'm looking at is my CloudTrail logs for that date, and now I have a simple query to run. So I'm going to quickly run that query to see who is accessing my cloud environment, and I'm going to skip through any VPN, company VPN information, so that I can only look at the external ones. At this point, I know these are IPs, but I do not know how to figure out where that traffic is coming from. So this is an example where I can collaborate with my colleague. So I invited Zafar to say, hey, can you help me with setting up some tools? And he's going to quickly help me by running a command that I do not know, by setting up a library. So this is a scenario where you may to do impact analysis, you may need multiple libraries, some of those tools that your team is comfortable using, and to get to the bottom of a situation. And this demonstrates where setting up your libraries that are needed for you to do your job is pretty straightforward and quick in this collaborative environment. So we are going to run who is on that, and we kind of found that some of these 35s, which are a lot of them are coming from Amazon. We can look at what type of activity they are doing. This is pretty harmless, so we are going to skip through that. But there is another IP that has heavy activity. So I'm going to look at who that is, and we are going to see that these requests are coming from Amsterdam. So this is just an example of process. So by running through these different steps, we were able to figure out that this is an activity to use some stolen AWS keys to spin up a spot fleet within our infrastructure, and incurring a lot of cost to the organization, so that they could do some crypto mining, which is a type of cost for us. So at this point, we as part of this triage process, we were able to get to the bottom of that the cause, and we are going to, as next step, we are going to rotate those credentials for the compromised keys so that we can save some money from an unnecessary spend. So the important piece is the triage process needs multiple teams to collaborate. So as we demonstrated with the runbooks that we created, we were able to accomplish that, and you can continue to build those runbooks, right? So to kind of quickly put together what you just saw for threat analytics data lake architecture with Databricks, first thing is, Howard mentioned about being able to take in all kinds of data and being able to keep that data in an economical way in the cloud infrastructure. So for volume of that data coming from for all kinds of audits that are happening with the size of the government and infrastructure that is out there, and varieties of the data that is coming in, we can accommodate all of that and then create a queryable data lake, right? At the same time, the important thing is with the scale of the compute environment, as well as being able to perform in a way that you can actually continuously stream these infrastructure logs and timely insights to make sure that you are basically acting upon those threats is vital. And we demonstrated that we are actually able to take these streams and generate these alerts, right? With the low cost, faster to analytics, with less friction, your teams will be able to augment some of the limitations that you get from traditional SIEM tools that you may have in your organization. And at the end, the important piece is with the collaborative multiple languages support and being able to share these runbooks, you can build a center of excellence around triaging process for a variety of scenarios for faster response process, right? So, I'm going to go ahead and hand off to Zafar to show you, how you can build a ML model on some of these advanced threats that are kind of, happening around, in this space, and how you can actually be prepared to build these models using Databricks platform so that you can plug more and more anomalous, detection functions into this overall architecture. Thank you. Zafar, I will hand it over to you, and thank you all.
Thanks, Arun. Now that Arun's shown how you can build out your cybersecurity data lake, I'll be showing how to build and deploy a model with the Databricks platform. And the model I'll be showcasing is a DGA detection algorithm, and just a little bit of a history on DGAs and what exactly they are. I'll start off by discussing the typical workflow of how a malware infects a computer and where the DGA domain generating algorithm mechanism kicks in. So what you'll have is a cyber criminal. They'll send out a phishing email to potential victims. The victim will just mistakenly download a file containing malware, infecting their machine if they open up that email. And once their machine is infected, it will reach out to a C2, which the attacker, command and control, which the attacker controls. This is typically, historically, I should say, a IP address or a domain name that would be hard-coded in the malware's binary. And once the machine does that and communicates to the command and control can sending instructions to the malware to spread more malware within the network, to do things like log keystrokes, remote control that machine, and start exfiltrating data. Now, as good guys, once a malware spreads and we've reversed engineered that malware and we find out the command and control, we could block those command and controls servers in our firewall. And what this would do is it would render the malware inert. It would no longer be able to talk to its upstream command and control and no longer perform malicious acts within our network. So to get around this, in 2009, one of the most important innovations in malware was created with the DGA algorithms, and it started with the configure worm. And this mechanism, instead of having a hard-coded IP address or domain name in the malware's binary, Instead, the malware would have an algorithm that would generate pseudo-random domain names. And it would make a passive DNS request to see if one of these had been registered. And the attacker, knowing the list of possible domain names that can be generated, would pick one and register it. And once the machine sees that one of the random domain names that it's generating has been registered, it will use that as its command and control. And the attacker can start sending malicious commands down to the server or the infected host. And as good guys, we can do the same thing again. We can block the malicious command and control, but the malware will just continue generating new domain names. And this could be a list of, tens of thousands or even millions of domain names that it could possibly generate. So the attacker just has to generate or register a new domain name that the malware is looking up, and it will use that. And this process will continue to maintain persistent control of the malware. So the types of DGAs that are out there, there's a variety of different DGA families that different types of malware use. There's ones with like redundant substrings or redundant dictionary words appended together. And there's ones with high entropy, just a random mishmash of characters. And these are very different than the everyday domain names. Just as a person looking at these, I can see that these domains don't look like the domains I visit daily. So what we can do is we can train a machine learning model to be able to pick up on these automatically generated domains and alert us when hosts in our network are reaching out to these. And in this example in particular, I'll be focusing on these domains with higher entropy, building a random forest model to be able to detect those. And there's also neural network approaches, which I've linked to in my presentation for being able to detect these wordless DGAs as well. So why should we care about, detecting these DGAs within our network? Pretty much any modern malware family will use the DGA mechanism as a way of accessing command and control, or as a fallback command and control mechanism. And ransomware attacks is a common, ransomware malware is a common type of malware that uses DGA algorithms for command and control. And it's causing quite a bit of damage both in the federal government and the commercial sector with these new types of malware. And if we can build a model that can detect DGAs, we can detect new types of malware that, whose binaries can't be identified by our endpoint detection systems because they use a common attack mechanism as older types of malware with these DGAs. So going into my notebook where I'm building my model, the first thing I'll get started with is when doing cyber ML projects is taking a look at the latest academic research. I've linked to some papers here around research around DGAs and how we can do feature engineering and build DGA classifiers to be up to the latest and greatest that the attackers are doing. So to get started, I'll start by building a training data set that contains labeled legitimate domains as in DGA domains. I'll get started by importing koalas, which is if you're familiar with Python, pandas, it's a way to distribute that across an Apache Spark cluster. And I'm also importing MLflow, which is a machine learning lifecycle management tool we've open sourced here at Databricks. And what it does is it allows you to log metrics, parameters, and artifacts from your model so you have reproducible experiments and easily be able to push models into production. And for the actual building of my model, what I'm doing is I'm importing a Alexa data set of 100,000 Alexa domains, and I'm storing that in a Koala's data frame. And Alexa is just a list of the most popular domains on the internet ranked by popularity. So these are my legitimate domains for my training data set. And you can see here, I'm doing some feature engineering to remove the TLD. And I'm also appending a legitimate tag so I can tell my model that these domains are valid domains. Next, I want to bring in my DGA data set. And with these DGA algorithms for these older malwares, most of them have been reverse engineered and the source code has been published online. So you can see, you can look up the algorithms and use that to generate your training data set, which is what I did here. So here's an example from I believe Endgame published some of the Kraken malwares, and you can see here the DGA algorithm is just appending a bunch of random characters to generate a domain. So you can run these algorithms to generate these domains locally to generate your list of malicious domain names. And there's also sample data sets out there as well. So now I bring in my DGA domains into my data set. I tag these as DGA. And you can see here, again, it's very different than the standard domain names that you would visit daily. So now I want to start doing some feature engineering to give my model some features to be able to key off on if the malware is a DGA. And I'll start off with some simple ones such as length, the length of the domain name, and entropy, which is the number of unique characters in the string. So you can see here the DGA domains, they tend on average to have higher entropy than our legitimate domains. So I'm getting some features that the model could key off on. And you can also see and they also tend to have a higher length than our legitimate domain names. Next, I want to do n-gram frequency analysis. And again, this is something I picked up on the research publications I read for being able to pick up on if a domain is a DGA. And with n-gram analysis, what we're doing is that we're comparing sequences of characters, 3 to 5 characters that occur within the words to a list of our Alexa domains, which is our valid domains. And I'm also bringing in a list of dictionary words to compare n-grams against. So again, just checking if our domain has sequences of characters that occur within valid domains and dictionary words. So I'm doing my n-gram function here to just count the number of n-grams. You can see words like Beyonce and Dominoes. They have a lot of matches of sequences of characters that occur within those that are in dictionary words. So you can see the words like bay here, once. With Dominoes, you have nose and Mino. So these are other sequences of characters that occur within valid domains that also occur in dictionary words. Whereas with my ones with high entropy, you can see here, we don't have any matches for this string. And then we have one match for this string in dictionary words, probably this NUH here. So you can see we have another feature now that we can key up on to see if our domains are legitimate. And you can see the n-gram matches for legit domains versus our DGA domains is much higher. So now we have some features to be able to go ahead and train the first iteration of our model. Here I'm removing some of the valid domain names that might confuse our model. So these are some domains that are valid but look like DGAs. So I'm removing these here. Next, I'll go ahead and train my model. I'm just doing a random forest classifier for my first iteration of my model. And now that I've trained my model, I can start testing it. And I'm going ahead and sending in these random strings to test it. And you can see my model. It's predicting a DGA for this one, legit for this word Beyonce here, and so forth. So I see the results of my model. Now that I have a model, I want to be able to put it into production. Arun showed you earlier building your cybersecurity data lake, ingesting data. And my model's no use to me until I can operationalize it. Otherwise, it's just a science experiment. So what we want to do is for incoming hosts or domain names we're reaching out to from our network, things like our passive DNS requests, our web proxy logs, our Bro HTTP logs. We want to check if the domains occurring in those data sets are DGAs, and we want to tag them as DGAs so we can trigger alerts. And if we see machines in our network reaching out to our DGA domains. So here I just have a DNS data frame here, and in order to operationalize my model, it's just a single line of code. I have a Python UDF for my model, and then it's with column prediction. So I'm creating a column called prediction, and I'm sending in my features that I engineered, the length, the entropy, the Alexa n-grams, the word n-grams to that model, and then I'll get the results. So in closing, we have our data scientists and our data engineers, they can develop and deploy a model. And now we've developed and deployed that model. We can start sending alerts to our incident man tracking system, and tools like Splunk and ArcSight for our cyber operations analysts to be able to start looking through and investigating if any suspicious domains are being reached out to within our network. And we can do this without putting any existing load within our SIM infrastructure and be able to do this at scale with petabytes of data. And again, in closing, you know, our adversaries, they're always innovating, and in order to stay ahead of them, we have to be able to take the latest research being published by academia and be able to operationalize that. Thank you.